Okay, yeah, we can see Wannes now. Can't hear you, but I think it's okay. Yeah. All right. Maybe we should start. So for today, we have Mark Langteau with us. Mark is a senior researcher, sorry, at DeepMind, who I think has been one of the first multi-agent researchers in the company. He has done a lot of games work in the past. Before with Mike Bowling, then at Maastricht University, in London at DeepMind, now again with Mike, I guess, and many others at DeepMind, and it's really great to have him here. He's actually the main inventor and developer of the OpenSpiel framework, and it's yeah, as you will notice, it's really a great software framework to do RL research in games. And he's here today with us to basically give you an initial tutorial on how to get started with it, and maybe give some glimpses of everything that is possible. Mark, with that, I'm happy to hand over to you.
Okay.
Yeah, let's just get going.
Okay, thanks a lot for the intro, Carl. So today I'll tell you a bit about a project I started a while back, actually. Internally at DeepMind, actually it was mostly a hobby project for me to do work in the multi-agent in games. And it slowly grew over time. And I think the first thing I want to do is just thank all these amazing people. And it's amazing. I've given a few talks of OpenSpiel now, and every time I show this, this group of people, these were the people who were involved with OpenSpiel really at the start. But like the group of, the group of people who have become involved with OpenSpiel has really grown a lot since then. So let me tell you a bit about OpenSpiel and the history. Its initial release was in August of 2019. The idea is that it's an open source framework for research and reinforcement learning, search and planning in games. The main implementations are like the core of the library is in C++, and a lot of the functionality is exposed through Python. Since then, we've developed a number of other language APIs that sit on top of this. So for example, Julia was a contribution actually. So there's a Julia API if you're interested in Julia. There's also a few other APIs that we've worked on internally. So we have a few people in the on the team who are interested in Go, and they've developed a few Go bindings around OpenSpiel, and we released those last year. And actually, just this past Christmas, we released a Rust API as well. The library has grown actually to be quite big. So when we first released it, there was only about 25 games, I think, and 15 algorithms or something like that. And it's grown to quite large over the years, thanks to a lot of amazing contributions and continue to work internally. So what's the idea? OpenSpiel gives you a general way to express multiplayer games. So it supports any n player games. It crosses the span of games in many different ways. So for example, there are zero-sum games, there are fully cooperative games, there are general-sum games. There's also perfect or imperfect information games, so partial observability or full observability games. You can look at simultaneous move games, in which all the players act at the same time. And actually, just as of last year, there's been a new type of game that we've supported, which is mean field games. So I'm just going to put this here to have in the set of slides. So if you want to look at the website, we're actually going to take a tour of the website in a few minutes. And we're going to look specifically at the contributors list, the games, and the algorithm, just to give you a small tour of the website. But we'll get to that in a few minutes. I want to show you a few things that we've done with OpenSpiel, or that you could do with such a library. So having a general games library is interesting, and I'm going to tell you why I think it's useful for research. But I'm going to show you a few of the things that we've done even at the time that we were releasing it. So it's really nice, and this was a contribution actually by one of Carl's older students, who's now at DeepMind, Daniel Hannes built a graphical library for kind of visualizing any game that's in OpenSpiel, including imperfect information games. So I find this to be very useful, especially for when you're going to show a game in a paper, for example. You can design like a small version of an imperfect information game. In this case, it's a Coon Poker, which is a common benchmark game that's used in the literature, and you can explain it graphically, right? So this is a picture of all the decision nodes. Those black nodes are chance nodes. Those blue nodes are nodes where the player 1 makes a decision, and the red ones are where player 2 makes a decision. The diamonds are kind of the terminal payoffs that you get in the game. So this is really useful to have like generic tools that can show you visualizations of any program. Also, for example, suppose you have a replicator or some other evolutionary dynamic and you want to characterize its behavior in, for example, a 3-action game or a 2-action game. We have visualization tools for that. So this is just some of the visuals. But maybe the main question is why have just another games or RL library out there? So I'm going to tell you a bit about the motivation behind OpenSpiel. So the idea, a lot of it has to do, of course, with my personal interests. I developed what was Spiel that became OpenSpiel because I'm interested in general multi-agent RL, and in particular, if you look at multi-agent reinforcement learning, the history of it has always included games. All of the classical problems are in game-like environments or can be formalized as extensive form games, even if they're multi-agent grid worlds, for instance. I wanted to make essentially the Atari learning environment of multi-agent games. So like I think what the Atari learning environment brought, one of the reasons I believe we've seen such an explosion in kind of like a interest in AGI and general deep RL is due initially to this Atari learning environment where researchers can develop algorithms that are kind of environment agnostic and go off and train their learning algorithms on like a general suite of different games in the Atari framework and compare the performance of their algorithm across these different games, right? And so you can design a learning algorithm and then compare, like, okay, in some games, our algorithm, performs well because the game has a certain structure, and in others it's harder because the exploration problem is just hard, for instance. So I've wanted to look into general game learning. So there's been a number of game competitions in the community over the years. And at least the biggest one, the general game playing competition that I could think of, has really focused on like not the learning part. And so I think I wanted to make a project where learning was like reinforcement learning in particular was kind of at the forefront of what you would use this library for. Games also have specific requirements and use cases. So this might not be obvious at a first glance, but for example, the dynamics of games are not always fully aligned with many of the reinforcement learning problems, like the classical RL problems. So for example, in games, potentially only a subset of your actions are available at any time, but maybe you have turn-based dynamics. So on a given, when it's one time and when it's one player's turn or an agent needs to make a decision, it might be like, for example, player 1's turn or player 2's turn, and two different agents might be controlling the decisions made at player 1 or player 2. So there's some special use cases that a lot of the RL frameworks that actually didn't support out of the box. So like it was quite difficult to take, for example, a DQN agent that was designed for Atari and just get it to work on one of your just pick any game. And so OpenSpiel has, for example, implementations of the standard RL agents that are that support these specific use cases for games. And another thing I've seen, so I come from the games community primarily. I've done a lot of games research in the past and a lot of computational game theory. Since being at DeepMind, I've taken a turn towards reinforcement learning, and I realized that there's a lot of There's a lot of common formalisms and a lot of common ideas that happen between these communities, but these communities don't always talk to each other. Or the people in the communities don't always meet and say, hey, look at some of the common frameworks or ideas that we're using. So I was hoping OpenSpiel could serve that purpose as well. And of course, I think over the past few years, especially open code, at conferences, some conferences are really making a push to kind of require almost code being submitted with your papers. We're doing a lot more like scientific progress as a result of building on code. And reproducibility has been really important in research, especially over the past few years. So that's my reason, or a bunch of reasons for OpenSpiel existing. Okay, let's talk a bit about the actual project itself, or the code. So we designed it with two main philosophies. One is to keep it simple, and two is to keep it light. So keeping it simple means you might find algorithms in OpenSpiel that are not heavily optimized. And if you were to go and write a custom implementation of those algorithms, they might be faster. We took this choice because we want OpenSpiel to be like friendly to newcomers. So for example, counterfactual regret minimization is not an algorithm that most reinforcement learning or classical reinforcement learning researchers would be familiar with. But we believe at least the implementations in OpenSpiel are simple enough that anybody with any background can go in them and kind of understand what that algorithm is doing. The second one is to keep it light. So that's one of my personal really strong preferences, is to not have too many dependencies, so that the project is easy to install. And I would say we made a very big milestone progress on that last year when we were able to finally install OpenSpiel via PyPy or pip, because that was actually non-trivial given OpenSpiel's structure of being based on C++ and exposed through Python. I'm happy to say that you can do that now very easily, and you can install OpenSpiel in just under a few seconds. So the main idea is that you have, partly for performance reasons, you have a C++ core. So most of the games are implemented in C++, and there's a Python API that's exposed for like higher level language, like higher level algorithms. And like I said, there's other APIs as well. The games are mostly written in C++, although we have much better compatibility now for Python games. And there's algorithms in both languages. So the nice part about the games being written in C++ is that any higher level language, for example, Julia, Go, Rust, whatever, can have access to all of the suite of games. And there's many examples. So I think it should be easy to learn. And here's an example here on the right of how you would basically play like through a game, where there's just two cases where you sample from a chance node to determine like the flip of a card, and you take every agent always takes like their first action. Okay, so it has an object-oriented API. So there's a number of objects that if you were to make a new game, for example, you just have to write a subclass for them. So there's a game. A game can have a subclass called a simultaneous move game, and then there's a set of functions that make sense only for simultaneous move games. From the simultaneous move game, a special type of simultaneous move game is a normal form game, and a special type of normal form game is a matrix game. So it's a two-player normal form game, and each one of those game types has a function called new initial state, which lets you create a new state in the game, and with that state you can go and sample episodes. All of the games have game type, a specific game type, which determine like its dynamics, for example, and it's whether it's imperfect information, how the rewards are represented, and things like that. Okay, so now I'm going to jump over to Colab just to show you some of those basics. So now I have to check and still, okay, we're still good. Okay, here's the website. So if you go to DeepMind on GitHub, if you go to DeepMind/OpenSpiel, here's what you're going to see. I'll just show you give you a quick tour of the website. If you want to install OpenSpiel locally, you can go here and follow these install instructions. What's nice, I think, is you could do a lot of what you want to do over Colab quickly. So introduction to OpenSpiel, if you want to be reminded of some of the basics. I'm just going to go here. If you want to take a look at some of the games we included, we have some of the classics here like backgammon, chess, hearts, hex, liar's dice, coon poker, Leduc poker, tic-tac-toe, for example. And so you can find just a list of games here if you're curious. Same thing with the algorithms. So many of the tabular methods for imperfect information games, so like CFR, counterfactual regret minimization and its variants, the classical search methods like Monte Carlo tree search and Minimax, some of the optimization algorithms that we want to use for computational game theory, and then like a lot of the standard first reinforcement learning algorithms. Okay, and alpha rank, of course. Yeah, I forgot to mention some of these evaluation or visualization tools down here. Okay. Yeah, so the first thing we're going to do, and I don't have this tutorial Colab up shared on the page yet, but I will make it available in the next few days. So I'm just going to go through this here. So this is the OpenSpiel tutorial Colab. So the first thing that we're going to do is just, it's going to connect, I think, automatically, yeah. It's just install OpenSpiel here, so it's going to connect to some runtime. And we're just going to wait a few seconds here. Okay. It was really nice because the previous students, like last year, for example, had to wait, I think, about 10 minutes for this step because we had to compile from source. So thanks to a lot of amazing open source tools and a lot of help that we got externally, we're able to now ship the binary through pip. So that's really neat. Okay, so let's start with part one, OpenSpiel basics. Let's take a look what this looks like. Okay, so first thing is, once you have OpenSpiel installed, you can import PySpiel. That's what you're going to use mostly to kind of query games. And I was just curious. I think when I was going through this, I was actually curious to see like how many games we had gotten up to this point. So like we have gotten 84 games. Quite amazed by how that's grown. Here's how you make a game. So once you've imported PySpiel, you can just click on game is equal to PySpiel.loadGame, and then you give it a tag or a name. And here you go. So it's going to load a game, and then you can print the game has a string representation, which is just the name of the game followed by any parameters in a bracket. So this tic-tac-toe doesn't have any parameters. So it just prints out tic-tac-toe. So let's take a look at a few properties, like basic properties of the games. Okay, so we haven't created any states yet, but the game itself has some properties. So for example, how many players does it have? So tic-tac-toe is a 2-player game, so this function will return 2. What's the maximum utility that any player could get? That's a 1. So in tic-tac-toe, if you win, you'll get 1. The minimum utility is -1. So if you lose, you get -1. If you tie, both players get 0. And the number of distinct actions. So the number of distinct actions is going to be a constant. It depends on the game. And it's going to be, the actions are going to be represented as integers, and they're always going to be between 0 and the number of distinct actions -1. So in tic-tac-toe, for example, you can put a stone on any one of the 3x3 board. So there's 9 positions. So each one of those actions corresponds to where you want to put a stone. So you can think of it also, by the way, as the width of a policy head. So if you were going to run something like AlphaZero, the policy head would have a fixed width. So the fixed width would be 9. Okay, so now we want to create a state, let's say. So we're going to create an initial state using game.newInitialState, and then we're just going to print the state, and here we have an open empty tic-tac-toe board. So let's just print out a number of things on the tic-tac-toe board. For example, there's the current player. The current player ID start at 0, so the first player is player 0. There's a function called isTerminal. That's going to return either true or false. So the game is terminal only when it's ended. So right now it hasn't ended. The game hasn't ended. It just started. At any time in the game, you can call this returns function, and that's going to tell you the cumulated reward for player 1, for player 0 and player 1. Right now, no players have gotten any rewards. So this is going to be 0. And in many of the OpenSpiel games, it's going to be the case that you don't get any rewards throughout the entire episode until the end. But if you did, they would show up in this vector. And there's also a vector called rewards, which is the one-step version of this. Okay, so states also have legal actions. So in this particular case, all of the actions are legal because the first player could put a stone anywhere they want. Okay, so let's play through a game. So in tic-tac-toe, the actions are encoded like this. The top left is action 0, and the bottom right is action 8. So what we can do is we can make a new initial state, and then we can call a bunch of functions that just change the state. So let's do that. So the first one is we're going to apply action 1, and then when we print the state, we see that X has put a mark up there. We've also printed the current player again. So now the current player has moved from 0 to 1. We can then put a number of marks in sequence. So this is like, player 2 will take action 2, or player 1, I should say, should take action 2, player 0, action 4, player 1, action 0, player 2, action 7. And then when we print the state, we can see that the first player has put down a row, or a column, I should say, of X's. So that's what that state corresponds to. It then becomes a terminal. So then his terminal becomes true. And you can get individual player returns instead of the vector by just calling this function instead. So the player 0 is a win for player 0. So they will get a return of 1. And we have a special current player when the state is terminal, which is -4. Okay, so that explains the output there. Let's just do this for a different game, just for fun. One of my favorite from the general game playing competition is called Breakthrough. It's really a neat game where it's a chess-like game where you have only pawns, and the object of the game is get to the other side. But the pawns have slightly different movement and capture rules. So here's your printing a state. So this is what the breakthrough state looks like. You have white and black, and it's played on an 8x8 chessboard. Now games in OpenSpiel are parameterized. So up to now, we've only created, for example, tic-tac-toe and breakthrough with their default parameter values. You can make a breakthrough game that instead has only 6 rows and 6 columns. And then you can print the state. So here you go. Now we have a 6x6 breakthrough game. And every time you create a state for this game object now, you're going to get a 6x6 state. Okay, so a little explanation of the actions. If you print out the legal actions here, you're going to just get a list of integers. And so this list of integers might not be very informative, right? They're kind of opaque. The number of distinct actions in breakthrough is much higher than in tic-tac-toe. It's 432. So if every game supports this action to string function, which lets you go through each one of these legal actions and actually prints like a string version of that action to kind of explain what it means. So action 74 corresponds to move A5 to A4. So this would be A5 here to A4, for example. And every game supports this. So if you want, for example, you can just, if you want to understand what is happening in a game, one of the first things you can do is write something that just samples uniform actions, prints out each one of the legal actions, and kind of observes what happens in that game. And actually, I should have mentioned that, you can do that. Every game has one of those. We call them playthroughs. Let me just see if I can find it. In integration tests, playthroughs, yeah. So if you're ever curious about what a game looks like on the surface, you can just click through some of these playthroughs, and it has some information about them. So Connect 4, for example, is a perfect information game. There's 2 players, number of distinct actions, etc., and then it kind of plays through the game, and then prints it out. So that's useful. Okay, so that's part 1. Let me just go back and collapse this. Yeah, so we have to go on to, we have to make it through 4 parts. They're not all as long. So let's now move on with the slideshow. Okay. Okay, so that was really just the API basics. So like some really basic properties of the game in the States. I think interestingly, so reinforcement, OpenSpiel is a reinforcement learning, or is a project about doing reinforcement learning in multi-agent RL. So I think one of the important parts of it includes like a learning dynamics library. And if you look at the community on multi-agent reinforcement learning, an important part of that, an important part of the literature on multi-agent reinforcement learning looks at how learning dynamics evolve over time as a function of these like rules that agents would use. So in the early 2000s, this is one of the first papers on this, along with a lot of evolutionary game theory papers that show if you try to do what would happen if you try to do policy gradients in, for example, like the simplest form of multi-agent reinforcement learning domain, which would be like a matrix game. And a lot of what was done at the time, and I'm assuming a lot of the stuff that you're going to see in your course, kind of looks at the dynamical system that results as putting 2 learners together. So here's some diagrams that can get drawn. Like you have these, you can characterize some of these dynamical systems, and you can show as a result of this characterization, are there fixed points? Are those fixed points stable? So will agents kind of like naturally learn to move towards like one specific fixed point? Are they unstable? One particularly like popular one is based on evolutionary game theory, and it's called replicator dynamics. So you can characterize the way that a dynamical system learns or moves as a differential equation. So this is like this on the left here. This is like a time derivative. You could think of it as a population is going to choose like a certain type of strategy or action in the case of like a matrix game. So, and what this differential equation is trying to do is describe how to change that the policy, or like think of it as the proportion of players that play that policy or that action in a population over time. So roughly what replicator dynamics is doing is it's going to increase the proportion of the action A as a function of how well it does to some degree, right? And we're gonna characterize this as if I were to switch entirely to using action A and playing against the population. So this pi bar here, this bold pi, is just like think of it as the average population number. So if I were to switch to completely start using only action A instead of using my stochastic policy that mixes or that uses the distribution over many actions, this is the utility I would get on the left here. And you compare that to if I were to use my policy as it is now, again with this entire population, and you could think of this as a utility that I would gain if I were to switch entirely to using action A. And it's roughly, you take this utility difference and you multiply it by the proportion that you're taking action A already, and this describes how your policy changes over time. And so what was done a lot in this literature was, shown, okay, well, now we have these, 2x2 matrix games, we can actually start, showing these vector fields of, how points in the space would actually change. So a point in the space you should interpret as like the probability of playing like action 1 in a 2x2 game for player 1, like X, and for player 2. And then as you move, like the replicator dynamics would describe how a point in the space would be likely to evolve. So you can see these kind of nice little fixed points over here. And over here, there's like unstable dynamics. And there's a really nice paper by Carl and some of the students that wrote like a survey of all these dynamics that used in multi-agent RO. Okay, so let's go take a quick look about how we do use this stuff in OpenSpiel. We're still connected. We'll expand part 2. Okay, so here we go. We import PySpiel again. Now you can create matrix games on the fly. So this is might be recognizable to some of you. It's called matching pennies. There are matrix games in the library as well, a lot of the classic ones, and we'll use one in a second. But I did want to show an example of how you create one kind of on the fly here using this create matrix game. If you try to print this game, you'll notice that I only included the utilities. So it doesn't have a name. So it's just going to use some kind of a default name. Now you can actually create, so it may be a bit strange to think about a state in a matrix game, but you can create an initial state. And when you print it, the only thing it's going to show is that whether it's terminal or not, so the game actually hasn't happened. You can always think of a matrix game as a one-step simultaneous move game. And it has row actions, which are automatically determined because we didn't include them in the create matrix call. And we have the utility matrix that we just made. Okay, so you can call all the same kind of functions that we called earlier. Like you can see what the current player is. We have a special ID for the simultaneous move player, which is -2. So in those states, you can actually query the legal actions for each player separately. So, player 0 has legal actions 0 or 1. Player 1 has legal actions 0 and 1, and the game is not terminal. So you can apply an action just like before, except in this case, instead of calling apply action, you would call apply actions, plural, and you include a list of actions taken by each one of the players. So this corresponds to that top left entry in the matrix. If you were to print whether it's terminal now, it's going to be terminal, and then you can look at the returns. So the API, as we saw before, still applies even for matrix games. You can just think of them as one-step simultaneous move games. Okay, so let's start looking at evolutionary dynamics. So there's a little project folder here called EGT. From there, you can import dynamics. You have a nice little helper function here called games payoffs array, which converts any OpenSpiel matrix game into a NumPy tensor. So that's kind of neat. And you have these dynamics called single population dynamics, and you can pass in the replicator dynamics. So for example, if you create a point here on the array, you can actually look at what the values of that pi dot is with respect to this specific strategy. So in this particular case, we've made a rock, paper, scissors game. There's 20% rock in the population, 20% paper, and a lot of scissors. So the best response to this population would be to play rock, because scissors is rock, paper. Yeah, scissors is overweighted, and so we have a positive differential on the rock strategy. We want to take away some of the scissors strategy because we want to take away some of the paper strategy because there's too much scissors in our population. And at this point, since we have exactly 20% and 20% of the other strategies, we do not want to change scissors. So what we can do is we can kind of simulate this by choosing some discretization, for example, like some step size alpha, and then we can just watch what a point in this population and how it would evolve. So first thing we would do is over here, add 10% of this gradient, you can think of it as, and increase the population of rock players, decrease the paper probability, and this one won't change. But now, as a result of that, we've overweighted slightly rock from its 20%, 20%. So the next version of that derivative will be to remove a bit of the scissors, but still mostly stays. Okay, so that's just a quick whirlwind tour through some of the dynamics. You can take a look at some of the neat dynamics inside here. There's much more. There's more than just replicator dynamics, but I think that's a classical one, so it's interesting to look at that. Let's now talk a little bit about extensive form games. Okay. Okay. So I want to tell you a bit about imperfect information games. And I'm going to do that by making a relationship to Markov decision processes, or I'm going to start from Markov decision processes. And I'm going to tell you a bit about some of the terminology that that we've used in the extensive form game setting. So you can think of an MDP. This is a very simple Markov decision process with 5 different states. The capital letters correspond to the states, and the small letters correspond to the actions. And then you'll notice that there's some probabilistic transitions. So if I start in capital A and I take action A, then I'm going to end up either in state capital B or state capital C.
Hey, Mark, I think there was a question
Oh, yeah.
in the chat. I don't know if you can see that.
I can see it, but I'm going to... I have seen that the player IDs are sometimes negative numbers. Yes. Are they special kinds of players? Yes, they are. So there's a -1 belongs to also where, yeah, I'll tell you where to find that. -1 is the invalid player. So we use that in a number of places. -2 is the simultaneous move player. I forget what -3 is. And -4 is the terminal player. Where do you find that? It's been long enough that I might actually not find it. But let's go take a look. It's in one of the main headers. I think it's in Constance. No. Spiel globals. That looks promising. Here we go. Boom. Yeah. So the -1 is. Oh, sorry, I got that wrong. -1 is the chance player ID. -2 is the simultaneous player ID. K invalid player is -3. Well, there you go. I've been using K invalid player throughout the code for a long time. I thought it was always -1, but it wasn't, which is great. I don't have to memorize this mapping. It's a great question though, and a lot of the answers to those style questions are actually going to be. A lot of them are going to be contained in Spiel.h. Spiel.h is kind of like, I would say, one of the first stops if you're looking for like what a function does. Even if it's a Python function, it's essentially going to be a Python function that's wrapped to call one of these C++ functions here. So here's the actual state object. And I think below is the game object, so you can see all the functions there. But yeah, good question. Okay. Yeah, Carl, if you see that again, I somehow didn't hear the trigger.
Yeah, I'll keep an eye on that. No
I'll make sure to go answer them all too.
Yep.
All right, so you can think of this MDP. I'm going to invite you to think of this MDP as not an MDP, but a multi-agent system. And it's a multi-agent system because we're going to invent a player that we're going to call Chance. And Chance is a player that plays with a fixed stochastic policy. I'm going to ask you to think about games this way because many of the algorithms that use extensive form games are going to walk over the tree that explicitly encode, or explicitly, I should say, represent Chance as a specific player. Okay, so these capital F and capital G now, we've added 2 new nodes. Well, we've added 2 nodes where Chance is a player that acts. Okay, and so we're going to talk about a few other things, a few other terminology. This is called a terminal. So now you can actually represent a history. A history is just a sequence of actions from start to finish, as just a sequence of these characters or a sequence of these actions, including Chance's action, right? The nice part of including chances action is now you don't have to actually store, for example, like a random number seed anywhere to kind of have a completely reproducible history. So in any game that explicitly represents chance in this way, you can now describe a history that takes you from the top of the game to the bottom of the game by just including all of the actions. So this action here that would sample to go to node B would actually be encoded as an action. And in OpenSpiel, it is. Here's another terminal history, for example. And here's what's called a prefix history. So if you have a history that's actually just a subset or a subsequence of any terminal history, that thing is called a prefix. And it could take you from, for example, the root node of the game to a specific spot in the game. Okay, so let me tell you a bit about partially observable zero-sum games. There's a common one that I showed you earlier called Coon Poker. It's very simple. Players start with 2 chips, and each one of them antes a single chip to play. There's only a 3-card deck that contains Jack, Queen, or King, and there's 2 actions. You can either pass or you can bet. And the reward that you give an agent is at the end of the game, they're either going to have won or lost some money, and it's the difference between how much money they have after the game versus before the game. And this is really what I wanted to get to. A decision point in these kind of games is called an information state. And really, you want to think of it as a state. It's like what the agent knows at that point. So it's always with respect to a specific agent whose turn it is, but it's everything they know at that point. And so you take out everything that they don't know. So here's an example. If you start the game of Coon Poker, each player antes a single chip. If I'm player 1 or I would be player 2 in this case. I would observe that I get the queen of the 3 cards, and then player 1 bets, meaning they raise. So they put in their second chip. This is called an information state now. It is my turn to act. I don't know what the other player got, but I know that it has to be either the Jack or the King because there's only 3 cards. Okay, so policies in these kind of games are defined over these things called information states. And these are can be formally defined. They're basically the set of histories, of prefix histories, that are possible given all of the observations. So this queen here is the private observation. So at any given time, the environment is one of many possible world states. These prefix histories that I told you about, you can think of them as world states. So it's the state of the world. For example, in this case, it would be whatever player 1 actually got as their private card. But as player 2, I don't know what that is. Yeah, so just emphasizing again, these histories are like the full histories of actions, including chances action. So you can formally define those. Okay, let's go take a look how imperfect information games are represented in OpenSpiel. All right, so let's open up OpenSpiel or import PySpiel. Let's load a new game, Coon Poker, with its defaults. I should say one of the parameterizations that's common across the games is the number of players. So for example, Coon Poker has typically been analyzed with 2 players, but if you were to put players equals 3 here, you would get a 3-player version of Coon Poker. Okay, so in Coon Poker, there's only bet and fold, so there's 2 actions. And what's interesting is it starts at a chance node because, as I told you, each player gets 1 private card. So if you print the state out, the state, you're going to make a state, you print the current player. As I said before, or as we looked, the chance player is not -1. And you have a special function here called isChanceNode. And this will be true in this case. So you can also call, by the way, legal actions here, and the legal actions would give you 0, 1, and 2. But at chance nodes, you have additional information, which is the distribution over each one of those events. So for example, there's an event 0, an event 1, an event 2, and they all have probability 1/3. So now if I just choose So what you'd normally do if you're doing reinforcement learning here is you would sample one of those outcomes, or some tree search algorithm. You would maybe walk over those and somehow include the probability in your algorithm. But because we're just simulating, we can actually just choose one of them. So we're going to say we're going to let the first player get the jack. We're going to check, okay, we're at a chance node even after we've applied that action, which means there's two chance nodes that follow each other, and they represent essentially the first player getting a card and the second player getting the card. So right now, the jack is no longer in the deck. If so, is chance node is true. If you print out chance outcomes, there's going to be two chance outcomes, the queen or the king, and now they have a probability 1/2 each. So you can apply the action, and then finally, after those two chance nodes, it becomes player zero's actual turn to act. So then you can print the state. You could print the legal actions, which is just 0 and 1, which correspond to pass or bet as their string representations. And the other thing you could do is print out their information state string. So every player in an imperfect information game at some point will have a string that corresponds to its information state. Right now, it's very bare. It only contains the card that it was dealt. So no actions have happened. All we know as player 0 is that we got the jack. So our information state string is just 0. But for example, we can start taking some actions. We can check once we take an action, for example, pass, it is player 1's turn. And now we can print out player 1's information state string, which is they got the queen, which is the number 1, and the first player passed. So this is what information state strings normally look like. They just contain, like the private information followed by like the sequence of actions. If you're using neural networks and you want to work on RL, at any point you have something called a information state tensor, which is just think of it as a 0-1 representation of the information state that you can pass to the input of a neural network. So this encodes for like the first 3 digits here correspond to which card was sampled, and then from then on it's a sequence of actions that we're taking. They correspond, sorry, to the some version. It's in the Kuhn documentation, in the Kuhn poker documentation, I should say. Okay, so I'm just keeping an eye on time. There's 2 more cells to do here. There's another game in here called Leduc Poker. It's a 2-round poker game. It is slightly larger in the sense that it has 3 actions. What this does is create a new initial state, print the state. You'll notice that in Kuhn poker, the state is slightly more complicated because we keep track of which round we're in. Player is also the chance node. So we can say, okay, the first player gets the jack, second player gets a second jack, and in the Leduc poker, there's actually 2 jacks. And we can then print the player again, and it'll have returned to player 0 at that point. Okay, and we can print the information state string and information state tensor, and you'll notice that they are slightly more complicated in the case of Leduc, but they essentially correspond to the same thing. So, it'll contain things like the round, which player is to act, which private card that I got, and here's again a 0-1 representation of that. Of the same information. Okay, so we can check until the second round. So check just means like call, right? We don't put in any money, and then it becomes like round 2. There's another chance outcome, or there's another chance node at round 2, because in Leduc you have actually a public card. So you can sample, for example, that would be the queen, sorry, of the first queen. And you can see here now in the information state, actually this is in the state string. If you print out the state, you can see that the sequence was call. And you can see this as well in the information state string down here. There's a round 1 and there's a summary of the round, how it went. So 1-1 just corresponds to call, because the call or the check action was action 1. Okay. So that was a tour through imperfect information games. I just have one small thing left, which is how to do reinforcement learning in OpenSpiel, and it's fairly quick. The only thing I wanted to say about that, suppose now you're going to want to do some reinforcement learning, so you want to go off and train some agents. There is actually an environment API that looks a lot like Gym. Now, the only thing that is doing different is that it's keeping, for example, the game and state objects that you've seen so far inside of the environment. So the way that you do this is you instantiate an environment, you give it the name of a game, it then goes off and creates this game object and maintains the state inside of this environment. And it exposes an RL API that looks a lot like the common ones that are used. On the agent side, you have also these things called abstract agents, and those things take in observations via these time step objects. There's many of them. So like here, I'll just give you an example. There's a random agent that just acts uniformly randomly. There's a Q learner that implements essentially Q learning. And the way that the Q learner learns is by interacting with the environment. And the environment goes back and forth between whichever agent is assigned in either player 0 or player 1. And it sends to the agents these time step objects, which essentially include the observations and the rewards from the last time step. And then the agents just submit back actions, and those actions are just essentially integers that correspond to the actions in the legal action set. Yeah, so that's it. I'll just show you one little quick last one here. So as I said, in the case of RL, you import this RL environment. Here's our tabular Q learner. We're going to create an RL environment, and you give it a game string. This is used in a number of places, the number of players, so you can just get that from the environment. You can get what's called the action spec, the number of actions from this action spec object, which is just like a struct, I think, or a dictionary, I think, of a number of information about the environment. And you just create the agents. So we're going to make 2 Q learning agents, one that's going to sit in player 0 spot and one that's going to sit in player 1 spot. Here we go. And here you go. You can train self-play Q learning agents in just a few lines. So this will look very familiar probably to people who have used any Python-based RL libraries. You have a reset function in the environment. While this time step object has a lot of information in there, while it's not the last time step, get whoever, and this is the difference, right? In the case of games, you get whoever the player is to go, like currently if you're using a turn-based environment. So let's run this thing because it'll take a few seconds. And you're going to get an agent output if you call your agent with this step function. The step function is giving the information that you got from the environment and collecting the output, which essentially has the thing that you need the most, which is just the action. And then you apply this like step on the environment with this action. At the end of the episode, you need to call the step function on all the agents because there's some learning algorithms that might not have finished their learning steps. So even though the episode is over, at the end of each episode, learning agents need to have this extra step called here because then they can apply like a learning step. Okay, so we've trained self-play Q learning in tic-tac-toe. Let's see if it can beat the random player. Here we go. This is importing a random agent. And we're going to say the evaluation agents is going to be equal to our agents that we just trained above, and a random agent named Entropy Master 2000. So the environment step looks very similar to the one above, the training one. There's going to be one main difference, which is that when you call your evaluation agents, typically you give this evaluation equals true flag. And certain learning agents will change their policy based on whether they're in evaluation or training. So for example, a Q learning agent will use an epsilon greedy policy when it's training, But when it's all trained and you want to go evaluate it, it's going to typically set epsilon to 0 and then just choose greedily. So let's see what it can do. So now we have our Q-learning agent in seat 1 against our random agent in seat 2. Path. All right, here we go. It takes the middle. That's always sensible. Random takes O. Oh, and it's starting to make a line. Let's see if it's smart enough to continue. All right, our Q-learning agent wins against the random agent. Okay, that is pretty much all I had. I'm just going to finish with 2 small slides. Here's a pointer of some examples that are going to be useful, I think. So when we put up the slides, you can refer to some of these examples. There is a paper that you can take a look at. So if I've used a lot of, particularly if I've used a lot of game terminology that maybe seem not familiar, I would say take a quick look over this paper. It'll explain some of those terms and give like a kind of an introduction to extensive form games. But otherwise, that is the end. Thank you for listening, and I'm super happy to take questions. Oh, I will say one more thing before I take questions. Please, please, by all means, if that was really fast and you didn't, it was hard to kind of understand everything, and if you're going through, if you're using OpenSpiel and you're going through something that seems not very obvious, please don't hesitate to open an issue here and just ask. We do have a nice community that's gonna that can help with things that are like, you will probably hit some snags that people have hit before. So please just ask questions. Feel free to, you can email me directly too if you want. But I encourage you to also post on GitHub.
That's really great, Mark. I think first of all we need to thank you. So big thank you for being willing to give this tutorial. I think we're running out of time, but I see some questions. So I don't know. Do you still have a few minutes?
I still have time. Yeah.
Yeah.
I'm
okay.
Yeah. So yeah, thank you, Mark. Great overview. Gets better every year, even.
Thanks. Okay. A few questions. Let me now stop. Let me stop sharing my whole screen and go back to sharing. I find this like fractal thing very off-putting. All right, and I'll share individual things as I go answer. Okay. Okay. I've seen the players. Okay. Yeah. For when we get to the code, can we draw a flow graph for the rock paper scissors game?
I didn't spot that question while it was asked. Sorry,
Otherwise
I would have interrupted you. But yeah,
a flow graph for rock paper scissors. Yes. If by flow graph you mean that those like dynamic, those like triangular dynamics graphs. Yes, you can do that in essentially the same way that you would in the 2-player case. I didn't do it in the tutorial. Send me an email if it's not clear how to do that. But you can find that in the visualization parts of the library.
I think it's very straightforward, right?
It's in code/viz, I think. Okay. Small practical question. OpenSpiel is now easy to install by pip. I know that when installing it by source, you can add the poker engine with OpenSpiel. Yes. Okay, so yes and no. For the question is, can you include, like when you're building OpenSpiel or when you're installing it from pip, can you enable conditional functionality? The answer is mostly no, but for this specific one, for the poker one, and for Hanabi, which are typically marked as conditionally compiled, we set it to on. So if you're curious, poker, universal poker is available via the pip package, and same thing with Hanabi, both of which are conditionally turned off when you go to install by source. So unfortunately, because of the way OpenSpiel compiles, you can't do that easily with the other flags. But it doesn't mean it's impossible. So if you really want to do it, just email me or ask online, and we'll answer there. But definitely for the case of poker, it's already included. And the game, by the way, is called Universal Poker. Do we have access to the slides? Yes, I will make the slides available. It might just take a few days, but I'll put the slides up for sure. Could we have the Python notebook? Yeah, absolutely. I designed the Python notebook with the intention of sharing it. It's a slightly more elaborate version of the example that we have online. It's not in the repo now, but it will either be in the repo by the end of the day or tomorrow, worst case, 2 days from now. Do specific replicator done, and it'll be linked on the main page as well under the tutorial. There's going to be a tutorial video. We're going to release this video as well, and it'll be there with the tutorial. Do specific replicator dynamics correspond one to